Good morning, everyone. Thank you all for joining us today for our webinar on accelerating econometric modeling using MathWorks tools. I'm delighted to have the opportunity to share all these valuable insights with you. My name is Tatenda, and I will be joined with my colleague Edward from MathWorks. As economists and researchers, we understand the critical role that econometric modeling plays in unraveling complex economic phenomena, making informed decisions and predicting future trends. However, there are challenges that are posed by the increasing complexity of economic systems, the exponential growth of available data, which can hinder our modeling efforts. That's where MathWorks tools come in. MathWorks offers a suite of powerful tools, including the MathWorks Econometric Toolbox, which is specifically designed to assist economists and researchers in overcoming these challenges. With its advanced functionalities, these tools streamline the econometric modeling workflow. They enable us to process data efficiently, estimate models accurately, validate assumptions effectively, and derive meaningful insights. Today, we'll explore the capabilities of these MathWorks tools and delve into the econometric toolbox rich features. We will discuss how these tools can revolutionize our approach to econometric modeling, enhancing both the speed and the accuracy of our analysis. Throughout this presentation, we'll focus on practical examples, which provide you with actionable knowledge that you can immediately apply to your own research and analysis. By no means are the things that we're going to go through today exhaustive. There are a lot more features that we're not going to have the time to go over within the time that's been allocated to this webinar, but we'll be happy to go over those if you reach out to us. By the end of this webinar, you would have gained a comprehensive understanding of how to leverage these MathWorks tools to accelerate your econometric modeling. You will discover new possibilities, improve efficiency, and elevate the quality of your economic analysis. I encourage you to note any questions that you may have or anything that you may find useful to the work that you do. Your insights and contributions will help to enrich our collective learning experience. Once again, thank you so much for joining today, and let's get started. On the agenda today, we have a part 1 and a part 2, which will both be led by demos. I will go through part 1, whereby I'll be accessing data to the SARB-Web API, working with time series data, and using a low-code modeling workflow to estimate a vector autoregression model. Edward will go through part 2, where he will estimate Bayesian vector autoregression models, go through DSGE modeling tools, and using models from SAMNet, before we close off with a conclusion. Moving into our MATLAB environment, here we have two scripts. The one script is going to be downloading and pre-processing data. The other script will be estimating the vector autoregression model. Both these scripts are going to be available to you at a later date. So MATLAB live scripts are interactive documents that combine the MATLAB code with formatted text, equations, and images within a single environment that is called the live editor, which is what we're looking at right now. So in this first one, we're going to be downloading and pre-processing data. And the data that we're going to use is going to be obtained from the SARB-Web API. The South African Reserve Bank hosts a large amount of data from its database that can be accessed through their website. This includes data that they have collected themselves, as well as data collected from other sources such as Statistics SA. They offer an application programming interface that facilitates the pulling of this data and the graphs that they host on their websites using various endpoints. You can think of an application programming interface as a middleman that allows two software components to communicate with one another using a set of definitions and protocols. For our case, the SARB data servers contain the data that we want to use for our modeling, and the code that we use is going to be able to fetch that data and bring it into our MATLAB environment. For this exercise, our data will be obtained from the tables that contain the data for the real sector. The API can return complete tables as well as full account statements and the time series for each line item using a column code, the time series code. First, we'll need to fetch the tables. To do this, we're going to use an API that we developed internally. We called it ResBank Econ Data, which is short for Reserve Bank Economic Data. And this allows us to fetch the data efficiently. It will also be available to you at a later date through File Exchange. Once we fetch the data, the table for the real sector looks like this. Here we can see the various columns that contain the data that we may find useful. For our specific example, we're going to need the time series and the measure name. These are found in the columns TS code and measure name. After we get the time series code, we will then use our API once again to get the more granular data. Within the MATLAB code environment, you can change the number of years or the date range that you want to use to get the data using a slider that can be found in the Live Editor tab where it says Control here. The numeric slider allows us to be able to change the value of a variable without having to type it out, which reduces the amount of code that you have to write. Once we specify the number of years that we're going to use, we'll use some simple datetime functions to be able to fetch the current date and also shift that current date to specify the number of years that we want to get our data for. When we specify the start and an end date, we're going to then fetch the time series data. And once we have fetched that table, it's going to look like this. The columns that are of interest to us are the period column and the value column. The period column and the value column need to be isolated. And to do this, after we've downloaded our data, we'll need to pre-process. So the data that we get from the SARB data server is in a table format. It's easier to work with timetables when we're doing econometric modeling, so we have to convert to these. We also want to keep only the important columns from the time series table, which is the period column and the values column. And since our loss frequency data is quarterly, we must ensure that this is consistent across all timetables. In this code section here, we're simply specifying the columns that we want, converting our data into a timetable, and also changing the frequency of the data that we have. An easier way to do this is use a data cleaner. We know that a lot of the data that we may find when we're doing our econometric modeler is dirty and it would need to be cleaned. Fortunately, the majority of the data that you can get from the API is clean. When this is not the case, you can use the data cleaner app within the MATLAB environment. Once you open it, it will look like this. You will need to import your downloaded data, and the two options that you have are either to import from a workspace or import from a file. And since you have downloaded the data to the workspace, it should be available in the workspace. You click on the data that you want to clean and import it. Once you have imported the data, it will immediately plot the data that you would have imported. If the data that you imported has more than one variable to it, you can simply select them here to view them at the same time. An added benefit of the Data Cleaner app is that it will give you some summary statistics on the right here, where it will tell you what type of data you have, the number of values that you have, as well as some statistics such as minimum, maximum, mean, median, and mode. To get more detail from your summary statistics, you can simply switch to the data tab within your data cleaner. That is going to show you more summary statistics as well as the data that you're going to be looking at. The summary tab does the same thing. This data cleaner app also allows you to clean missing data, clean outlier data, normalize the data that you have, smooth your data, as well as retime your timetable. In our case, we needed to change some daily or monthly data into quarterly. We'll be able to do that within this app, as well as many other features that include reshaping the data that you have. Once you're done with your session here, you can export to your workspace or generate a script to be able to do exactly the same functions that you've just done without having to open the data cleaner app. Once you have cleaned the data, if your variables exist as independent tables, you may want to combine them. To do this, you can use MATLAB live tasks. For this example, we're going to need the synchronized timetable tasks. This can be found under Live Editor, where it says task. You have many other tasks that are available for you when you're working within the MATLAB environment. Some for pre-processing data, tables and timetables, integrating external languages influence as interfaces, as well as other tasks. For our case, we're going to need synchronized timetables, which can be found here. Once you click on this and you load it into your editing environment, it's going to show up as a control panel like this. You select the variables that you want to include in your table output, and then you simply run this section by clicking on this button here. The added benefit of using tasks is that it's not only a no-code environment, you can also view the code that is used to produce the results that you want. And once you have the table that you desire, you can choose to rename the columns into something more intuitive. This is what I've done in this code section here, whereby I changed from value investment to investment, and the same with the other two columns. The output table will look like this. Another very efficient and very beneficial task that you can use is the create plot task, which can be found under the same section. Create plot allows us to create various types of plots depending on the data that we have. There are many types of plots that are available to you, and you can simply search for it here or scroll down and find it. Select the data that you want to plot and run that code section once again, and it will give you the output that looks like this. This is a great way to start our modeling session by just viewing what our data looks like before we get into any estimation. Moving into the second script. The majority of the content in this script serves to demonstrate some of the interactive features and the editing capabilities of the live script environment. It allows you to use images as you've seen in our previous script. It allows you to also add equations and text with features such as bolding, underlining, using italics, and heading with the click of a button in this text section right here. This will be very beneficial if you want to create a report or if you want to use MATLAB for research. So for this illustration, we're going to be using the data that we obtained in the previous plot. It contains a timetable called economic data timetable with 3 variables, namely fixed investment, disposable income, and consumption expenditures in billions of rands from the first quarter to the last quarter of last year. This is 722 observations, and this is what we're going to use for inference. The data has been stored in a MAT file and can be loaded into the workspace with the following simple command. Once we have the data in our workspace, the next thing we want to do is to interactively model our vector autoregression. So the Econometric Modeler app is a MATLAB application that can be used for many econometric tasks, such as testing, estimating, and evaluating models. It can be started with either running this command in the command window or going into the apps section of MATLAB and finding Econometric Modeler. Once you open Econometric Modeler, you'll have to import your data. And for this, you're given two options. You can either import from your workspace or import from a mat file that you've stored on your local machine. To import from a mat file, you simply click on the data that you want to import and open. Once that is loaded, you can select the data that you want to load and import. Note that if you wish to start a new session in Econometric Modeler app and you want to import a different set of data, it will clear the previous section. It'll clear the previous session and the previous data. So you'll be starting from scratch with the new session. As you import the data, it immediately plots it into our viewing pane. When we have the plots in the viewing pane, we have some features that we can use to do some preliminary data exploration. One very useful feature that you can use is show recessions. This shows you the period in the data where there was an economic recession. To view our data more clearly, we may choose to use a grid. And to zoom into a particular period, we simply use the zoom in feature. Once you select on this, you highlight the period that you want to zoom in, and it will zoom in. Note that the time series is becoming more granular at the bottom here. You can continue to zoom in as many times as you want. If you want to go back to the default view, you simply click on the home button. If you want to view the time series on individual viewing panes, you can either select to right click and click on open, or you can simply double click. To view these time series simultaneously, you can simply drag each tab to a separate space in the viewing pane. By looking at this data, we can see that it exhibits an exponential trend, which means that before we can use this data to estimate our models, we will need to transform it. The Econometric Modeler offers four main methods of transforming the data that we have. Because our data is exponential, we need to take a log transformation. To do this on all our data simultaneously, you simply hold down the control button and you select on all the data that you want to transform. Click on log in the transform section, and it will show you a plot of the log transforms. To go back to the single view, you simply right click on the pane you want to view, go to tile all, and select on single. Once we've transformed our log data, we can still see that this data still exhibits a trend. To remove the trend, we may want to take the first order difference. To do that, we go back to the transform section and we click on difference. Now our data looks more stationary, but viewing it and estimating that it looks stationary like this is not enough. We may need to run some tests. To do this, we go on the test button. It gives us a drop down. We select on the time series first. It gives us a drop down which gives us the available tests that we can run on our data. And because we want to test for stationarity, we're going to select one of these. For this exercise, we're going to test using the augmented Dickey-Fuller test, or the ADF test. Once you select on this, you're given an option to edit the parameters before you run the test. We can run for one lag at the 5% significance level using an autoregressive model and a t-stat. We run tests for all the variables that we've transformed. To do that, we need to go back to the econometric modeler, click on new test. Once again, click on the ADF test. Go back to the ADF tab and run the test. Looking at the outcome of our test, it seems that our data is indeed stationary now. But to avoid confusion, we may want to rename the variables that we have in our time series tab. To do this, you simply click on the time series tab slowly twice, and then you rename them. Repeat this for all the transformed time series variables. Once our time series is transformed and it's stationary, it is now ready for us to run models on it. To do this, we once again hold down the control button and click on the time series that we want to use for modeling. Go into the models pane here and click on vector autoregression model because that's the one that we're going to use for this exercise. Once you click on that, a dialog box will show up that allows you to edit the autoregressive order as well as the lag. Note that as you edit the autoregressive order, the model equation is going to update. We're going to run a VAR model for three autoregressive orders. Once you're done specifying the parameters, you click on estimate. Note that a variable for each model, VAR1, VAR2, and VAR3, appears in the model pane, and the estimation summaries appear in the respective model summary pane. You can view the properties of an estimated model in the preview pane by clicking on the models pane. The next thing that we want to do is to compare the results and find the model that fits to our data the best. The estimation summary in each model summary tab contains a plot of fitted values and residuals with respect to the time series in the time series list, a standard statistical timetable of estimates and inferences, and a table of information criteria. To compare how well these models fit to the data, we'll need to compare the information criteria of each estimated model simultaneously by doing the same exercise of dragging it to a separate section of the viewing pane. The model that we're looking for is the one with the lowest information criteria readings. That would seem to be our VAR1 model. Once we find that, we want to rename our model and call it the estimated model. After we have estimated the model and selected the one with the best fit, we want to determine the accuracy of the model. For that, we're going to have to select the model in the models pane and then select on residual diagnostics. We have three main options that we have to us to assess the accuracy of the model. The first one would be residual normality, which can give us clues about the skewness of our data and possible outliers, as well as kurtosis. Autocorrelation can give us some clues about autocorrelation, and the heteroskedasticity can tell us about heteroskedasticity. When you click on one of these, it will show up in the viewing pane with the plots of each variable and how they've been fitted to the data. A model that roughly shows a normal distribution is one that we can expect to have a good fit to our data. Once we have assessed the accuracy of the model, we are now done with our session in our econometric modeler. And the next thing we may want to do is to export. We have several options that are available to us to export. The one we have at the right at the bottom would be a generated report. When you're generating a report, you're given the option to select which variables or time series you want to include in the report, which will show up as plots in the report, as well as which model you want to include. Once you have selected those, you're also given the option to select the output of your model, either PDF, a Word document, or an HTML. Another option that we have is to generate a live function of your session. The live function will show up in your live editor as every single activity that you were doing in the econometric modeler. And this runs code, this generates code that runs efficiently without you ever having to write a single line of code or comment it. You can add your own comments and tune this to your liking. The next option for exporting that we have is to generate a function. If you do not want to convert it into a live function, you can simply have a function that looks like this. As you can see, the code is well commented so that anyone else that you may share with this will be able to follow exactly what you are doing. And this is all done without you having to write a single line of code. The last option to export that we have is to export variables to our workspace. With this option, we can explore the variables that we have transformed in our econometric modular session, as well as the model that we have estimated. Once we have exported these variables, they're going to show up in our workspace on the right here. This will be useful in our later exercises of generating forecasts. Once you have those models in your MATLAB live editor environment, you can then use it to generate forecasts. For this exercise, we're going to generate forecasts and approximate a 95% forecast intervals for the estimated model, the VAR1 model that we selected from our econometric modular session, for the next 4 years. So for convenience, we're going to use the entire time series as a pre-sample for the forecasts. And the forecast function discards all the previous pre-sample observations except for the final 2 observations. Here we select the time series. We select the data that we want to pass into a model. Once again, using the MATLAB slider, we can change the number of periods that we want to forecast by simply using this slider and not having to text not having to use text to change the variable name here. Once we have selected these 2 variables, we can pass it into the forecast function with the model that we got from the econometric modeler. and the num periods, which is the number of periods, and the data that we want to use to generate the model that we're going to use for forecasting. Once that model has been generated, you're going to want to plot the data to see what it looks like. Once you plot the data, it's going to look like this in your MATLAB workspace, which is great because it shows you all the possible outcomes that could come from the model that you have estimated in the econometric modeler. Once you have generated the forecasts, you may want to determine causality by conducting a causality analysis. So you want to determine whether the series in the system Granger caused the other series by conducting one-step Granger causality tests. So to do this, we simply pass the estimated model into the Granger causality test function, and it gives the following output. According to this output, we can see that these variables generally depend on one another and cause a change in one variable which will cause a change in another variable, except for expenditure, which does not cause a change in income. And simply by running this one line of code, you're able to run all these tests and determine the causality, which is very simple and uses very little code. Note that our entire session that we just had in our Econometric Modeler app can be done in our editor by running functions that come from the Econometric toolbox. That's what this entire section of code does, whereby the first section, we're transforming the time series by taking the log and then taking the difference. In the second section, we're plotting the transformed time series. And then in the next section, we're going to test for stationarity using the KPSS test. In the following section, we're going to estimate our vector autoregression models. Note the usage of the equations within the live editor environment. Once we've estimated our model, it's going to look like this. And then we're going to use it to generate forecasts. Note that if you want to convert this into a report that you can share with someone else, you may not find it necessary to share the code with them as well. This is simply as changing the view of the live editor here, whereby this will hide the code, but still show the text and your session. This can be very useful if you're either collaborating with someone or you're generating research or reports for someone else to view. You also have several other options that you can use within Live Editor to export the session that you have just done within the Live Editor. To do this, you go to where it says export, and you have the option to export it to a PDF, a Word document, an HTML document, or LaTeX file. All these are only some of the features that are available to you using the Econometric toolbox and the Live Editor environment. There's a lot more that we won't be able to cover, but we'll be happy to go through with you if you reach out to us. Now that we've come to the end of our second script, we're going to move on to the second section, which is going to be headed by Edward, my colleague from MathWorks.
Right, thank you, Tatenda. As Tatenda said, thanks all for joining. My name is Edward. I'm one of the engineers here working at MathWorks. What I'm going to do is I'm going to move one step up. I'm going to start looking at a bit of the Bayesian approach to these models, and then I'm going to show you a bit of what can you do with MATLAB and what other tools are available for you on top of MATLAB to work on these problems. Right, so let me share my screen. Hopefully, all right. Hopefully, you can all see my screen. Let me know otherwise. So as I showed you, you can use the Econometric Modeler app to get a sense on like how these type of models are modeled in MATLAB, get started with the tool, and start doing some initial analysis to the problems. However, nowadays, when you start modeling the economy of an actual country, of a region, the standard vector regressions models fell short, and they're not enough to actually model the economy. And oftentimes people say, look, these models should have a Bayesian approach. What does that mean? Well, the approach is simple, right? So when you have a vector regression model of this form, when we say this model is Bayesian, we're simply saying that the coefficients we want to estimate are not fixed anymore. They actually have a statistics distribution. Now, the problem is that depending on what type of statistic distribution you think these parameters should have, the problem can be very easy to solve or actually very hard. Now, the way it works is as follows. You typically are after the conditional distribution of the coefficients given a set of observations. And to estimate that, we use the Bayes theorem. That's why we call them Bayesian bar models. However, in order to use this Bayesian theorem, we need to assume, or we need to consider a prior distribution or the initial distribution of the coefficients A. And that is the key of the problem, right? So depending on what distribution you choose for A, you will get a different distribution for the posterior problem, conditional A to the observations. Sometimes it's the same, sometimes it's not. And sometimes it's very easy to estimate, and sometimes actually very hard to estimate, right? Now, in MATLAB, there are 4 types of problems that you can estimate, called the normal conjugate, semi-conjugate, and diffuse Bayesian bar model. Now, the models are estimated using these functions that you see on screen, or you can use the generic function Bayes bar, where you can just simply say the type of model that you want to estimate. What I want you to show is that you cannot do these problems using the Econometric Modeler app. They're too complicated, but the process you need to follow is exactly the same. So if you estimate the model with the Econometric Modeler app and then you print the code, as Tatiana just showed you, you can do exactly the same process by just changing the function to a Bayesian bar model or normal bar model or the one you're after, and then estimate the model. So let me show you how you can actually do that. And then we'll talk about tools that augment that and let you explore even more complicated models. Now, before I move forward, just be aware that for those of you using state space models that have been in MATLAB for a while, in the same way that we introduced Bayesian bar models, now you have Bayesian state space models. However, we won't cover those today since there's no time. But those would be one option if you wanted to do, for example, some DSGE modeling within MATLAB itself. Now, to get started, let me just get some data. For this, same as I did, I'm going to get data, but in my case, I'm using data from the St. Louis Fred. So I'm using the Fred function within MATLAB, and then just pointing to the actual link of the repository. I'm grabbing some data, synchronizing it, and getting a bit of 3 variables, right? All synchronized, all cleaned up already, and I have inflation, unemployment, on interest rate. Now, the objective is the same, right? I want to estimate the bar model. So if I wanted to do exactly what I did, using a frequentist model, I would use the BARM function. I simply use BARM function. I say the number series I have, in this case is 3, and how many lags I want to estimate. And I put a slider here so you can just move around. And then I just use BARM, and then I get model, and then I estimate this model using the estimate function with the data set, and then I get the estimated model. It's all extremely simple. Imagine now we wanted to do it in a Bayesian form, right? So what I did is I created a drop-down menu with the 4 options that MATLAB has. Sometimes people call the normal model Minnesota, so I just call it that because it might be more common for some people. And then I created myself a function where I can pass all this information and returns me this model, right? So let me show you how this function works. In this case, I want to estimate the normal model, right? So the Minnesota prior, right? So it's a model where it assumes that the innovations matrix, or sigma, in the problem is a fixed value, and then it assumes also that the coefficients have a normal distribution, right? So the way to estimate this model is the follows: I select the generic function Bayesian vector regressive model, and then I say the model type should be normal, and then I apply some of the constraints that this model can have, which are commonly known as the self-lag, the decay, the cross-lag, and the element of scale. And the idea is that the bar model usually are specified as follows, and you can see how these variables map into the actual model of the vector regression. Right, so what I'm going to do is I'm just going to call this function, right? This is it's a slide function where you see here, it's called estimate bias barm, and then it has a switch statement, right? So by passing Minnesota, I'm going to be using exactly this code you see here, right? So once I estimate this model, you can see that I get an estimated model outside. Now, one of the properties of the Minnesota model, which is quite nice, is that because you assume that the prior model is of the type normal, the posterior, it can actually prove mathematically is also of the type normal, which is quite nice. It's actually a known distribution and it's a normal distribution, which means it facilitates our problem quite a lot. If it was not, right, it could be that, for example, if I get a diffuse barm as my prior model, my posterior is actually a conjugate barm. So the distributions are different on the prior and the posterior, right? So for now, let's just keep using the Minnesota because it's simple, and you can see that it's very fast to estimate. Now, the first difference you'll see once you estimate the Bayesian model is that instead of giving you a set of fixed values for the coefficient, what you get is obviously distribution. So if I just summarize the model, I get a mean and I get a standard distribution for all these parameters, right? And obviously, I also get an innovations covariance matrix for the error term. Now, typically, now that I've estimated the model, a very common analysis that people does is calculating the impulse response functions. That is saying what happens to my variables when I have a shock or an impulse in one of the others, right? For example, if I had a shock in my unemployment, what would happen to, in this case, the interest rate or the or the inflation, right? In MATLAB, you can just do this with the function IRF, and to apply this function, you need a bar model. So I construct a vector terrestrial model using the mean values, right, of my estimated Bayesian one. So I do that, and I get the impulse response functions. So if I plot them, you'll see that I get, because I have 3 functions, I have like 9 impulses in total. Now, this is, however, not enough, because now we have a Bayesian approach. So everything should have a statistic distribution of it. And this is just a mean value of the impulse response functions. So what do I have to do to get the actual confidence intervals? So in this case, I can compute them by either Monte Carlo or a simulation approach. Because in this case, my model is, my posterior distribution is known, I can simply simulate a lot of draws from my posterior distribution, get new values for the coefficients across the intervals, and then get the quantile of the response, which means it allows me to get a confidence intervals for the impulse response functions, which I can then plot and get a sense on how they actually how the statistics are affecting the impulse response functions. So obviously, at the initial point where the data is known, there's no distribution. And as I go further away in time, you can see how the confidence intervals become bigger and bigger as the uncertainty is more and more. So in the same way that what I did here, you can see how the process is the same. I estimate the model using bias barm instead of the barm function. Once I have the estimated model, I can compute forecasts, I can compute the error decomposition, the historical decompositions, the impulse response functions, all exactly the same you would do with bar, with a bar model, which you can do with the app. But in this case, the model is a Bayesian one. Now, as you keep moving forward in this process, it might be that these 4 models that MATLAB offers, they're not enough themselves to model the economy or to model the problem that you have. And you have a even more complex problem. For example, you can have a bar that varies in time, or you can have a bar that depends on the country, right? So it can be actually more and more complex. Now, one of the tools built in MATLAB that you can use for that is what's called the VARX toolbox. This toolbox is developed by some people working at the European Central Bank, and actually a lot more people, right? But it's you can use it in MATLAB itself. So to get it in MATLAB, you can simply go to the MATLAB homepage, and then if you go to add-ons, you will find it right there. The tool is free. You just need to have base MATLAB, and then if you type bear, you'll find in there bear 5.1, the little bear as an icon, and then you'll get a button here that says install. Now, in the same way as the econometrics toolbox, to use VAR, you can either use the command line options that is explained in the documentation, or you can just click on the icon here and get the user interface. Now, we update VAR quite often, right? So if you install it through the process I mentioned, every time there's an update, you'll get a little ring on this VAR up top saying, hey, you can get a new version for VAR. This is the documentation, and this is how you use it. So if you open VAR, that's what you see. You can see that VAR by default offers 6 different types of models to estimate, right? The OLS, or the least squares approximation, is the standard frequencies VAR model. So it's exactly the same that you would get if you in MATLAB go and say VAR and do the process that Tatenda showed you. The process will be the same. If you're more familiar using it in MATLAB, you can do it. If you're more familiar using it with VAR Toolbox, you can. There's absolutely no problem. The results will be quite similar. The error will be something around 10 to the -6, -7, due to because some of the matrix operations are done in a different order, but they're perfectly equivalent. If I'm doing a Bayesian model, in this case, you can see how VAR has a few more options. MATLAB has only 4. In this case, there's 6, and there's even more parameters that you can actually toggle on to estimate this model. Right, so the Minnesota that's selected by default is the one that I just estimated in MATLAB. So if I was using VAR, I would just enter the parameters here, enter what results I want. For example, do you want to calculate the impulse response function, conditional forecast, the FFBD, the historical depositions, and whatnot. And once you're done, you click run. Right? This runs VAR, puts the results in place, and gets you the final estimated one. So after VAR is done, so what VAR does, it prints on screen all the results. Right? As same as Tatenda, it shows you the big results. It shows you the variance covariance matrix, structural decompositions, and whatnot. And it gets you all the results in an Excel file, in a TXT file, and also the final workspace in a .mat file if you activate it, which I haven't. Or maybe I do. Wait. And at the end, it plots a lot of figures if you want to. There you go. Some of them plot a lot, right? With all the results that you wanted in there. Right, so let me close all these figures and move along. And I said, finally, you also get a mat file with all the variables in MATLAB in case you want to load and do some additional ad hoc analysis of your problem. So there's one tool, as I said, you can get it in there. If you have any problems, you can feel free to reach out to us. We'll be more than happy to help. We work quite close with the authors of this toolbox. And yeah, we'll be quite happy to help. The second common tool, or second famous tool in this space, is called Dynare. Dynare is a tool developed by a consortium of universities and central bankers that, again, it's meant to help you solve this type of problems. In this case, though, it's more oriented to solving dynamic stochastic general equilibrium models, also known as DSGE, as you can see here. The way this tool works is a bit different, though. This tool defines its own modeling language. So they invented a new language that will help you enter this type of autoregressive model in MATLAB. If I just open the tool very quickly, you can see how you can specify your endogenous variables, you can specify your exogenous variables, the parameters you're using, and eventually you can define a model block with your equations. Again, this is not MATLAB, this is a meta language, right? For example, when you put a parenthesis -1, it means that the lag one of the variable or the parameter CH. Now, how does this tool work? So once you run this tool, what Dynare does is it grabs this file and it transforms it into MATLAB code. And then actually gets MATLAB, runs the optimization and all the necessary mathematics, and gets you the final result. Same idea as VAR, or same as the MATLAB itself, just using a different approach, right? It facilitates entering the models. The editor is just right. The editor is not part of MATLAB. It's something I built for myself. Happy to send it if somebody actually wants it. It just helps me visualize the equations a bit, and I can indent and do some nicer, use a nicer interface, right? And then eventually you can click run. One of the advantages of this tool is that you can actually enter MATLAB code directly in here, right? For example, if you wanted to do some plots, you can actually directly enter MATLAB code in the same way you would in MATLAB. And then this tool would just grab it and add it to the files that it generates. Now, let me show you how this one works very quickly. So this SAMNet is a repository of models that are used for modeling and forecasting the economy, especially on the South African countries. So you can go to this website here, and you'll find a few models, and many of them are actually written in Dynare. So the web looks like this one. Let it load for a second. And if I go to the models, what I did as an example, I picked one from Liu and Molise. I think I picked this one, which is a model to extend, to draw some conclusions around the Basel III capital regulation. Now, if you look at this model, what you'll find is a .mod file, just that, right? So let me show you quickly what this file looks like, which you already seen, right? I downloaded this file, and you can open it with an editor. So let me open it. You can open it with a MATLAB editor, or if you have an editor that indents or like defines, can understand Dynare language, is even better. In my case, this looks the one I just showed you here. So that's the exact code that was on GitHub. Right? It's just text file with some meta language defining your model. Now, to run it, I can click run, but the actual way to run it, so what this tool is doing on the background, is simply running Dynare SAMNet.mod. And then this is the Liu Molise model I just downloaded. And then you can add some additional configuration properties next to it. For example, don't produce graphs, don't produce a log or something like that. But in general, this is enough. And then once you run it, same as Bear, it prints all the results on screen, and it generates some of the figures with the output, right? Again, the number of figures you get, the number of results, plots, and whatnot, depend on what how you define the model inside the tool. Right? So again, another tool, another type of models that you can where you can augment the possibilities of MATLAB, also built in MATLAB and quite easy to use. And finally, there's another popular tool for modeling economies called the IRIS toolbox. I'm not so much aware about this one, but I do see it used quite a lot in this space. So I wanted to just again make everybody aware that this tool exists. You can again download it for free on the internet, install it in MATLAB, and start using it. It's called IRIS, and again, it's another tool to solve the same type of problems: Bayesian estimations and DSGE models. It's entirely built in MATLAB, and again, it's free of charge for any one of you to use. So that's it. As Tatenda said in the beginning, if you have any questions, you're more than welcome to ask them now, or reach out to us after the webinar at any point. Please don't hesitate. We worked in that problem with other central banks quite often, and we're quite familiar with them. So we don't know more economy than you do, but we can definitely help you get the most of the tools as you work with them. So let me stop sharing, and then if there's any questions in the chat, I can answer them.
Thank you, Edu. So today's webinar has provided us with valuable insights into accelerating econometric modeling and research using MathWorks tools. We've explored some powerful capabilities of the econometric toolbox in the modular app in the editor environment, as well as the more complex things that Edu went through. So we offer comprehensive solutions to support you in your journey towards more efficient and accurate econometric modeling. Whether you need assistance in optimizing your code for speed, or ramping up your skills on MathWorks tools, or ensuring interoperability with other software such as Python, or further expanding your knowledge through workshops, we are here to help. Our vast array of resources include documentations, tutorials, and a supportive community that's willing to help you and assist you every step of the way. Moreover, MathWorks provides a large open license family, which allows for seamless integration between between teams and institutions. This ensures that you can leverage the full power of our tools within your research community, which fosters innovation and accelerates progress in economic analysis. Some of the universities that we have in our open license family is Nelson Mandela University. We also have Northwest University. We also have the University of Pretoria, University of Wits, and with some of these institutions, Optimum provides technical installation support with regular seminars and workshops for training your staff to be able to use these tools within your development network.
Yeah. But there was another question in the chat. Maybe I can answer that one since it affects Dynare itself. Somebody asked if how I installed the Dynare app. So basically, I developed that one for myself because I was getting a lot of requests from people wanting it to use. It's not out in the for the public yet, but if you send, as Tadenda showed here, an email to us or Tadenda itself, we can provide to you. It's just a double click on a file. If you want to use it in MATLAB Online, that's also possible. So yeah, just send them an email. They get in touch with me, and we'll send you the prototype so you can test it, play around with it. Give us feedback, hopefully, on how it works. What would you like to see in there?
Yeah. Thanks, Adrian. So I encourage you to explore offerings, connect with our experts, and take advantage of these valuable resources that are available to you. So we've come to a section where if we have questions or comments from the people within the attendance, we'd love to hear your thoughts. If you do not wish to speak, you can just write it out in the chat, and then we can attend to it. I see that our time is coming to an end. But if you do have questions that you did not manage to ask during this session, once again, we'll be very happy to address them if you reach out to us. There's some contact details on the screen right now. You can reach out to Optimum Solutions or myself directly with the emails that are displayed. And thank you all for being a part of this webinar. We appreciate your time in being here. We look forward to supporting you on your journey with econometric modeling and research. And we wish you all the success in your future endeavors. And may your research continue to drive a positive impact within the field of economics.
Yeah, there was a question on whether there's tutorials and other webinars. So we don't have a regular schedule for webinars, but there are tutorials on our website. So if you just go to Google and just put MATLAB on RAM, you'll get a 2-hour crash course free of charge on the internet and just to get started. You'll get an online version of the tool that we showed. So you don't need to install anything. It's just a website where you can use it completely. And there's a bunch of explanations on how to use this, that, and the other thing. And the same way, we have a basic tutorial for MATLAB. There's the exact same equivalent for the statistics package, the optimization package, which are build a lot of the functionality that's used for the problem we showed you today. Once you know that, the rest is knowing economics, and we can help you a bit there, but like it's not our expertise. We're expert on the tools, not on the economics themselves. Yes, I wanted the chat, so let me put the at least I can put the basic. That's the website.
We have a hand up. Memo. Oh, it's gone now. Okay.
Okay, I think we can. So that's the end of the hour.
Yeah, so that's our webinar up. Once again, all the files and the data that we used is going to be shared with you at a later date, just so you can experience some of these tools for yourself.
All right, thank you, everyone.